Hello everyone, welcome to lecture 20 on Mechanics and Materials 1. In this lecture we want to talk about the deflection of beams and shafts. We cover sections 12.1 to 12.3, 12.5 to 12.7 and 12.9 of the book. This is our only lecture related to the chapter 12 of the Hibbeler book. So in this lecture, essentially what we want to do is to find the so-called elastic curve or the deflection of beams. Now, if you think of a beam, whether it is clamped, supported, or it is an overhang beam or a simply supported beam, it doesn't matter. If you have that beam under loads, whether they are concentrated force or different types of loads, you can imagine that the beam will deflect, it will deform. Now, that deformed shape of the beam, we call that elastic curve. So we are looking for the function that defines the deformation as a function of x, and that function is the so-called elastic curve. Now in this lecture, instead of a function f, we call that v. Small letter v indicates deflection. So if you imagine you have an overhang beam here shown in the figure, and you have two forces P1 and P2 applied on it, you can imagine in the first portion on the left, the moment would be negative, and in the right portion on the right, the moment would be positive. So now in the first portion, where the moment is negative, it turns out that the deflection of the beam is also downwards. In part 2, where the moment is positive, it turns out that the deflection of the beam is upwards, or the curvature of the beam rather. Okay, so we are talking about the curvature. And in between, at point C, where the moment itself is 0, the curvature is also 0, and that point would be our inflection point. On the supports B and D, obviously the deflections are 0 because they are the supports essentially fixing the deflection. Now, the fact that we observe where the moment is positive, the curvature is upwards, and where the moment is negative, the curvature is downwards, it's not really surprising because this is exactly in accordance with the convention that we used for the moment sign itself. So if you remember, we assume that positive internal moment concaves upwards and negative internal moments concave downwards. So we kind of expected to see this, but now it's more clear. However, we are going to actually prove this and see this together in terms of the deflection function itself. So the same thing holds if you, for instance, think of a clamped beam shown in the figure. Now you have a force and you have a moment here. In this case, you can imagine, for instance, in the second portion of the beam on the right, the moment would be constant. So you would get a constant upward curvature in that sense. But then again, the point at which the moment is 0, you would have an inflection point. Another important thing about the elastic curve is how to handle the boundary conditions. You can imagine if you have pins or if you have rollers, your boundary condition would be that the deflection is 0. But if you are dealing with a fixed support with a clamped beam or a cantilevered beam, not only the deflection is 0, but also the derivative of the deflection is 0. So the derivative of the deflection is basically the slope of the elastic curve. Okay, equipped with this little introduction, what we want to do next is to calculate the moment curvature relationship. In order to do that, we proceed very similar to what we have done before. We assume a generic beam under different types of loadings. So you can have a concentrated force, you can have a concentrated moment, or a distributed load here. And then again, you can see the axes are like this. So the horizontal line from left this is our x coordinate, and the vertical line is our deflection coordinate v. What we want to do is to take a little increment of the beam, enlarge that, magnify that, and then look what happens inside that in order to find the moment curvature relationship. So if we take that little increment and enlarge it here, you remember what we have done before. We talked about the so-called neutral axis. And then on the neutral axis, we said that under deformation, the length of the neutral axis doesn't change. So that would be your length dx here, which you can also write it as rho delta theta or d theta. And rho is the radius of curvature. But then for any other line at any distance y from the neutral axis, the lengths will change. So here you would have ds prime, which would be rho minus y times d theta. So when you write ds and ds prime, you can also calculate strain, epsilon. And if you simplify that, you will see that epsilon is minus y divided by rho. So now we take that relation here. And what we want to do next is to use our knowledge or our previous derivations in the topic to kind of relate the curvature with moment. Pay attention that rho is the radius of curvature, and 1 over radius of curvature is actually what we call curvature. Okay, so this is the relation between curvature and strain. Now, if we use the material law, the constitutive law sigma equals E epsilon, you can write epsilon as sigma divided by E. And then if you use the Flexure formula that we derived previously in the last lecture, we proved that the Flexure formula reads sigma equals m divided by I times y, and y is the coordinate, is the distance from the neutral axis, basically. So the y is the coordinate measuring the distance from the neutral axis. You would have this relation. So this is the relation we were looking for. 1 over rho is exactly curvature, and here you can see the moment, and we were looking for the relationship between moment and curvature. But we are not done yet. What we need to do is to relate that also clearly to deflection and the distance from the support or x coordinate. So in order to do that, we need to use our mathematics knowledge and the definition of the radius of curvature. So if you have a function, let's say f as a function of x, and if you could fit a circle here, at that point, the radius of that circle is your radius of curvature. Now you can imagine this is a very mathematical problem. It has nothing to do with mechanics and materials one. So there must be a connection between the radius of curvature and the function itself. So we want that relation, how the radius of curvature is calculated for a given function, and this is exactly how it is done. Again, in the example I had, we just showed the function as f of x, but for us, that function would be v of x, and v is the deflection. So that relationship for the radius of curvature is this. So 1 over radius of curvature is the second derivative of v with respect to x divided by 1 plus first derivative squared, and then the whole thing to the power 3 over 2. Now, if you combine these two, you get this relation. So v double prime divided by 1 plus v prime squared to the power 3 over 2 is m over ei. But you can imagine if you have a long beam under deformation, and in this course we usually talk about small deformation, small strain elasticity, and with linear assumptions, you can imagine that v prime is not a very large number. Also remember that v prime is essentially the change of deflection with respect to x. So if you have here delta v and here delta x, so basically tangent of this angle would be v prime with a minus sign, maybe because it was downwards. But you can imagine that that angle, or let's say angle theta anywhere in this picture, is not a very large angle. So maybe it is, I don't know, maybe it is 2 degrees or something like that. So if it is 2 here, that is kind of maximum in this picture, and it is almost 0 here. So almost everywhere in between, it's something between 2 and 0, or between 3 and 0. So if v prime is a very small number, v prime squared is even smaller, it's negligible. So this term altogether does not play a crucial role. So if 1 is added with a very small number, you get basically almost 1 itself, and therefore we neglect that term. So if you neglect that term, you end up with this relation. So if you just assume all of it is approximately just 1, then this is your moment curvature relationship, except that now we don't have exactly curvature anymore. All we have left of curvature is the second derivative of deflection. Now, in this relation, usually we refer to EI as the flexural stiffness 2. Okay, so now that we have this, if you reorder the terms in the relation, we have our most important relation for today's lecture. So EI V double prime equals M. But also you remember that the derivative of M, the derivative of moment itself is the shear force. And the derivative of the shear force with respect to X is the distributed force W. That means if you differentiate the relation that we have here with respect to X, you would find a relationship between deflection and shear force. if you differentiate that again with respect to x, you find a relationship between deflection v and distributed force w. In summary, this is almost everything that we have learned so far. The important thing here is that we still use our plus convention, assuming that in the relations that we have here, the shear force must follow this convention, the same as moment and distributed load. Another important thing here is that the small letter v is deflection and the shear force is the capital letter V. So they should not be confused. This one is a small letter, this is deflection, and this one is capital letter V, that's shear force. Okay, so if you look at these relations and you go upwards, you can actually see that if you have a distributed load as a function of x, you can integrate that to get the shear force, and you integrate again to get the moment. Now, once you have the moment, you can divide that by EI. And if you do that, what you have here is basically V double prime. So now if you integrate once more, you would have V prime, which is essentially theta, because we assume that theta is small. So the derivative, or basically the tangent of theta and theta are equal. So V prime is the same as theta. And then if you integrate that again, you would get the deflection function itself. So what does this mean? It means that if you start from W, you integrate 4 times to get the deflection function. But also it means that you can come backwards. So if you have the deflection, you can differentiate 4 times with respect to x to get to the distributed load W. The last thing I want to emphasize here is again that theta is the derivative of deflection with respect to x, and it is measured with respect to the coordinate system and the convention that we are using here. So here in this coordinate system, pay attention that V positive is upwards and X positive is towards right. So that means that here, for instance, theta is positive, and if you think of theta here, you would have a negative sign for theta. And then again, the reason that we allow ourselves to say theta is the derivative of deflection with respect to x is that we already assumed that theta is a very small number, or otherwise we have assumed that tangent of theta is sufficiently equal to theta itself. Okay, so everything that you see in this slide is what you need to calculate the deflection of a beam, or to calculate the so-called elastic curve. What we are going to do next is to solve for elastic curve of a few examples together. Exercise 1 of this lecture is similar to problem 12.1 on page 582 of the book. The cantilevered beam shown in the figure is subjected to a vertical load P at its end. Determine the equation of the elastic curve if EI is constant. So you have a cantilevered beam. Your x-coordinate starts from here. Again, deflection is upwards as before. Here you apply a force P downwards. And the question asks to calculate the elastic curve. What we want to do also additionally is to calculate the maximum deflection or the deflection at point A and the maximum angle or theta at point A2. So we are going to also calculate this. Remember, the key equation here is EI V double prime equals M. V being the deflection. Okay, so as before, we start basically by cutting the beam at a distance x and calculate the moment and shear force. We don't really need to calculate the shear force. We need the moment specifically because for the relation of the deflection, we just need the moment itself. But also, if you wanted to calculate the shear force, it would be very simple. So V would be simply minus P here. But you can imagine that M is minus Px. And then again, all you have to do is basically to calculate the moment equilibrium. And what you can see is that M plus Px would be 0. So Px is because the distance x times the force P would cause a moment in the same direction as M. So if you assume this is your counterclockwise, it's the plus direction, you will have a plus sign in between, which means your M would be minus Px. So once you have the moment, and you already know how to calculate the moment, obviously, we use our relation for the deflection or for the second derivative of the deflection. Now, this is all you have to work with. You have your deflection or the second derivative of deflection as a function of x, basically. All you need to do is to integrate once to get the angle or v prime. Then you integrate twice to get the deflection function v itself. As you can see, you have two unknowns, C1 and C2, but you can also calculate them using the boundary conditions. Now, for this curve, the boundary conditions correspond to the right end of the beam, and that's where the deflection is 0, and also the derivative of deflection is 0 because it's a clamped beam, it's a cantilever. So these are your boundary conditions. Deflection at x equals L is 0. Deflection derivative or the angle at x equals L is 0. And if you insert these two into the equation that you have here, or into this and this equation, basically, you calculate C1 and C2. Now you insert C1 and C2 in the deflection function, and this is your elastic curve equation. That's all you wanted to calculate. But now, since you have the elastic curve equation, you can also calculate its derivative to basically compute the angle theta, and that would be the relationship for the angle theta in this problem. So if we want to calculate the deflection and the angle at point A, all you have to do is to insert the coordinate of point A into these equations, and the coordinate of point A is x equals 0. So if you insert x equals 0 here, you get the deflection at point A and the angle at point A. Pay attention that the angle having a power L squared and deflection has a power L cubed, which makes sense because deflection is basically in meter and the angle is dimensionless. So it's one dimension less in meter. Also, see that the deflection is having a minus sign, is negative, which makes perfect sense because you can see if you apply a force P, the deflection itself is downwards, but the angle is positive, which again, it makes sense according to what we said because it's the derivative of deflection with respect to x. All right, this is all you had to do for this problem. Exercise 2 of the lecture is similar to problem 12.2 on page 584 of the book. Determine the equation of the elastic curve for the beam shown in the figure, assuming that EI is constant again. So it is similar to the problem we just had before, except that now you have a distributed load, and also the support is not a clamped support. It's not a fixed support. So you have a pin here and you have a roller on the left. The key equation here is again EI. Second derivative of deflection is equal M. So the first thing you need to do is to calculate the reactions from the supports. If you compute the area of this triangle to calculate the effective force, that would be 1/2 of W0L. And due to the symmetry of the problem, you can imagine that 1/2 of that would be carried by each support. So basically you get W0L divided by 4 for the left support and the same for the right support. Now, due to the symmetry of the problem, we don't have to solve all of it. What we want to do is to start with the coordinate x from the left-hand side and only calculate the elastic curve for the first half of the beam, and that would be basically be the same thing for the second half. In order to do that, you need to calculate the moment m. For a section at distance x. So if you cut the beam at a distance x, you would have this figure here. So basically on the left you have W0L over 4. That's the force that we have, the support reaction. You have the shear force downwards. Then for that area, for instance, if you cut it here for this triangle, for the area of the triangle, you would have 1/2 times the distance x, that's the base of the triangle, and 2W0 over L times x, which would be the height of the triangle. So again, in order to calculate the height of the triangle, you can imagine that basically you have a line here with the slope 2W0 over L, and you multiply that slope by distance to get the height. All right, so if you do that, the effective force would be W0 x squared divided by L. which is acting on the distance x over 3 from the right end. So what you want to do now is to write the equilibrium of moment. So you write the sum of moments equals 0. That gives you, assuming that counterclockwise is plus, that gives you m plus what moment you get from the distributed load, which would be the effective load times distance, minus the support reaction times x, and minus because if you just think of the distance times the force here with respect to this point, it would cause a clockwise moment. Okay, so this is essentially your equilibrium of moments, and from that you get your moment equation. That is your internal moment as a function of x. So if we asked you to draw the moment diagram, this would be exactly the function that you would draw also as a moment diagram for this problem. But we don't want to draw shear and moment diagram here. What we want to do is to calculate the elastic curve or deflection, and basically that means that we want to just take that function m to our formula ei v double prime equals m. And if you do that, this would be now your point of departure. So you have the second derivative of deflection as a function of x. All you have to do is to differentiate, to integrate this twice to get the deflection function itself. Now, obviously, because you integrate twice, you would have also two unknowns. We will calculate those two unknowns from the boundary conditions, from the conditions on the problem. But before doing that, pay attention that you get a polynomial of order 5. This is not a surprise because if you look at your distributed load is linear. That means it's a polynomial of order 1. And if you remember, you need to integrate the distributed load 4 times to get the deflection, or otherwise you need to differentiate 4 times the deflection with respect to x to get the distributed load. So you expect the difference of power to be 4 between your distributed load and deflection. So it makes perfect sense to have a polynomial of order 5 if you have a linear distributed load. If you had a uniform distributed load, then the polynomial would be of order 4. All right, so this is our deflection equation, and we have two unknowns, and this is also our equation for theta. Now, if we look at the boundary conditions, maybe it seems that we have two conditions. One is here, so v at 0 is 0, and then you can also imagine deflection at L is 0. But this condition is not good. This is not helping us here, because remember, what we are writing here is only valid for the first half of the beam. We use the symmetry. We clearly assume that x is between 0 and L over 2. For the second half of the beam, we cannot use this. So we want to solve for C1 and C2 using the boundary conditions. But the second boundary condition must also be between 0 and L over 2. That means the second boundary condition for us, it would be the fact that due to the symmetry of the problem, we actually know here V prime would be 0. So now you have two conditions. From the two conditions, you can calculate the constants C1 and C2. Now, inserting C1 and C2 into your deflection equation gives you exactly your deflection polynomial or deflection function as a function of x. which is exactly the so-called elastic curve. Now, if you want to calculate, for instance, the maximum deflection which would occur at the center, all you have to do is to insert the coordinate x equals L over 2 into the deflection function, and that gives you the maximum deflection for this problem. And then again, pay attention that the maximum deflection has a minus sign indicating that it's going downwards. All right, so for this problem also, that's all we had to do. This is your elastic curve and this is your maximum deflection. Exercise 3 of this lecture is similar to problem 12.3 on page 586 of the book. Determine the equation of the elastic curve for the beam shown in the figure and also the maximum deflection. Again, we assume that EI is constant. So you have a simply supported beam. You have a pin at A and a roller at C. And at point B, 2 meters away from A and 1 meter away from C, you have a force of 6 kilonewton downwards. Point D here is assumed to be the point at which we have the maximum deflection. So we pretend that we don't know exactly if the point D is in the first half or in the second half. You can kind of intuitively imagine that point D must be in the first half or in the left half. It's not exactly half, so in the left part, which is longer. But we pretend we don't know exactly that. We calculate that distance eventually. But before that, we need to calculate the elastic curve itself. So in order to calculate the elastic curve, we need to start with calculating the support reactions. And then again, from the distances here in the problem, you can imagine that we need two forces, AY and CY, such that the sum of them would be 6 kilonewton. But then CY must be 2 times larger because the distances are 2 and 1. So with respect to point B, if you wanted to write the equilibrium of moments, you can imagine that the force at AY must be half of the force at C. So basically you would have these two equations and you calculate AY and CY, or the support reactions. Now again, assuming that we have a point D somewhere, we know that at that point where you have the maximum deflection, theta is 0, or the derivative of deflection is basically 0. In the figure, the point D itself is shown between A and B. Again, that is intuitively correct, but we will calculate it and we check if this intuition is actually meaningful. Now to proceed, we need to write the moment equation for each part and then again use our relation EI V double prime equals N. From our previous discussion in the last lecture on drawing the moment diagram, maybe you remember, if you have a figure like this or if you have a problem like this, you can imagine that because you have a concentrated force, you would have a jump of, let's say, shear force and moment on that point. So you may want to distribute the problem into two parts or decompose the problem into two parts or two coordinates. For instance, we can imagine that we have a coordinate x1 that is only valid between A and B, and then we have the coordinate x2 which is only valid between B and C. That's what we want to do. So you can do that, and then by doing that, again, you can calculate the shear force for the first part, and you calculate the shear force for the second part, and you know there would be a jump of shear force at point B because you have a external force applied there. Now for the left part, if you cut it anywhere between A and B, the shear force itself would be 2, and the moment would be 2 times x1, because you have a force 2 upwards and then the distance is x. So it would cause a moment like this. So your moment equation for any point between 0 and 2 would be 2x1. On the other hand, if you cut it somewhere here at any point between B and C, your moment equation would be 2 times x2. This is because of the force 2 at the distance x2, obviously, minus 6 times x2 minus 2. Obviously, you can imagine at the point where you apply the force itself, you only get a jump in the shear force, not in the moment. So if you assume x2 equals 2, you would get the moment m2 equals 4, which is correct because also the moment from the left part is also 4. Okay, so at that point itself, you don't expect a jump of the moment, you expect only a jump in the shear force. But then the moment equation itself, any point after that would be influenced by the contribution of the shear force. And you can also imagine that the shear force at any point here, we said it's 2 according to our convention, and then in the second portion, the shear force anywhere is minus 4. Okay, so having these, we have m1, we have m2, and now we use our equation EIV double prime equals m, where you have v1 and v2, indicating the relation for the deflection with respect to the coordinates x1 and x2. So once you have this, all you need to do is to kind of integrate them properly. So in order to do that, and in order to show kind of the two parts of the problem, we write it like this. So for the first half, your moment equation reads 2x1. For the second part, the moment equation reads m2 equals 4 times 3 minus x2, which means EIV double prime is that. Then you integrate it once, you get the v prime. You integrate twice, you get the v deflection. So now again, the blue equation on the left part, this is corresponding to AB, and the green part is corresponding to BC. So you have your deflection functions V1 and V2 so far. What you need to do is to compute the constants. But if you look at the constant, you have two constants, two unknowns on the left part, two more unknowns on the right part. If we look at the boundary conditions, well, the boundary conditions are simple here. The deflection at A is 0, the deflection at C is 0. So you got two conditions. But we need 4 conditions in order to calculate the constants, because we have 4 of them. Now, the other remaining constraints or conditions that we are missing here is exactly the compatibility or the continuity of the deformation itself. So you can imagine if you have a deflection, if you have an elastic curve like this, and this would be point B, at point B, whether you calculate the deflection from, let's say, the right-hand side or from the left-hand side, the deflections must be equal. But not only the deflections, you can imagine the derivative of the deflections. The slope of the lines, they should also be equal. Okay, so basically these are the two constraints or the compatibility constraints that will help us now to calculate the constants. So all you have to do here is to insert x1 equals 2 into this equation, and then also insert x2 equals 2 into this equation, and then calculate the v's and set them equal. The same holds for v primes. So in that sense, it would have made sense basically to assume that these derivations that we have here would also be valid at point 2 itself. So instead of having just strict inequality, we should have less equal or greater equal. The reason I didn't do that is because I mentioned before, if you talk about the shear force, this wouldn't be true. The shear force itself, it has a jump at point 2. So in the previous slide, since we also talked about the shear force, we didn't start with having equality. But in this slide, it would be perfectly fine to have the equality because we are talking about the quantities that are actually continuous at 2. M is the same, so the second derivative, first derivative, and basically the deflection are the same. All right, so once you do this, now you have 4 equations, 4 unknowns. You can calculate the 4 constants, C1, C2, C3, and C4. You can insert also those into your equations and calculate your deflection function for each side. But more importantly, what we wanted to do was to calculate the maximum deflection at point D. So in order to do that, and then again, assuming that point D is somewhere between 0 and 2, we set V prime at x equal xd to be 0. We do that, and then again, using actually the constant C1 and C2 in the function, we can calculate xd, which turns out to be 1.633, and that is less than 2, so this is okay. So point D, indeed, our intuition that the maximum deflection should occur in the left part is correct. And once you have that coordinate, you can insert it again into your deflection function, and you can get the maximum deflection itself, which in this case is minus 2.90 divided by EI. Pay attention that it comes again with a minus sign, indicating that it's a downward deflection. Okay, so this is everything we wanted to do with this problem. Now, what we want to do next is to talk about the so-called discontinuity functions, or an alternative approach to solve problems like this. So as you can see here, sort of the complexity of the problem comes from the fact that we need to split the problem into 2 parts. What we want to do next is to learn a method, a strategy that allows you to write all of this as one function together. But then in order to do that, we need to learn the so-called discontinuity functions. All right, the next topic we want to talk about is the so-called discontinuity functions. And as I just mentioned previously, these sort of functions are useful to avoid defining multiple coordinate systems, similar to what we did in exercise 3, for instance. So the first type of discontinuity functions that we want to talk about is the so-called Maculi functions. And the Maculi functions are defined as such. And these brackets are also sometimes referred to as Macaulay brackets. So this is basically the definition of a Macaulay function. If you have the argument x minus a in Macaulay brackets to the power n, this would render 0 for any point that x is less than a, or alternatively, it would render 0 if the argument is negative. So you can imagine that if you have Macaulay bracket of a quantity that is less than 0, that would be 0. But if it is positive or 0, so basically for any point x is larger or equal a, you just get x minus a to the power n itself. Now, the definition of the Macaulay function holds if n is larger or equal 0. So the power is larger or equal 0. An example of that is this. So imagine you have, let's say, the coordinates here, x and y coordinates. And this is, for instance, the point x equals 2. And at this point, you want to define a function. So a line which is starting at point 2, but then at any point before 2, your line would be just 0. So if you want to define this type of function, usually what you would do is to say, well, it is 0 if x is less than 2, and it's x minus 2 if x is larger or equal to. In terms of Macaulay bracket, this function is exactly x minus 2. You can imagine it has a power 1. So basically, this thing that I just drew here is essentially x minus 2 in Macaulay bracket. Okay, so that's why these functions are useful, because instead of writing a function in terms of two different arguments, you can just write it in terms of one Macaulay bracket. The integral of that then is also following the common integral rules. So an expression to the power n would be just what we do in usual integration. So we add 1 to the power and we divide by power plus 1. And then obviously you also get a constant. So this is the definition of Macaulay function. Now, if n is smaller than 0, the power, so it's for instance minus 1, minus 2, and so on, we come to an extension of Macaulay functions that we usually refer to as singularity functions. Now, these singularity functions, they render 0 for any point that x and a are not equal, and they render 1 if x and a are equal. So if we want to, again, draw this thing, for instance, if here is the point x equals 2, and you want to have a function that gives you 1 exactly at this point, and then 0 everywhere else, you would just write x minus 2 to the power minus 1, for instance. Now, if you have that, the integral of that is now kind of, it's not a standard integral in a sense, because the power n is minus. So for these ones, the integral is just the definition here. The integral of x minus n to the power n here would be just x minus n to the power n plus 1. Okay, so if we combine the so-called Macaulay functions and singularity functions together, we will have this picture. You can kind of see we have these Macaulay brackets, but in the upper part, in the green part, the power n is larger or equal 0, and here that power can be minus 1, minus 2, and so on, so it's less than 0. And as I mentioned again, these are very useful when we want to talk about problems that the loading is not continuous, that you have a jump in the loading condition. There is a table in the book which reads like this, and this table kind of shows why these Maculi functions are interesting. So for instance, you can imagine you're dealing with a problem like this. So if you think of this problem, the distributed load is 0 until the point at distance a, and then it's a linear function with slope m. So you can basically write your distributed load like this. W equals m x minus a in Macaulay bracket to power 1. So basically for any point after a, it would naturally give you just m x minus a. And for any point before a, it gives you 0. Now, why is that interesting? Because you remember that if you now integrate your distributed load, you get your shear force. And then you can integrate the shear force and you get the moment. And obviously, at this point, you remember the idea here always is EI V double prime equals M. So you want to have M so that from that you can calculate the deflection later. All right, so the last row makes perfect sense. Now, if you look at the previous row, it's a similar story. It's now just a distributed load that is uniform. So being uniform, it means it's very similar to what you just had, but instead of the slope, you have the value, the magnitude of that distributed load, and then power 0, it tells you it's a constant function, it's uniform. And then again, if you integrate that, you get the shear force. If you integrate that, you get the moment distribution. Okay, so the last two rows, now we know how to handle them. Now, if you look at this one, assuming that you have exactly this picture, the shear force here would be 0. So at any point on the left part of the point at which you apply the force P, the shear force would be 0. And then right after that, the shear force would be exactly P. So you can define your shear force like this. Shear force is V P x minus A to power 0. Now, again, that means if x is less than A, you just get the shear force of 0. And if x is greater equal A, you just get the shear force equal P, which is exactly what we wanted. Now, again, you can integrate that to get your moment, but you can also imagine that if you wanted to write this in terms of a distributed load, you can write it as a distributed load, but with the power minus 1. So basically from here to right, you could integrate, and then if you want the other one, or the one to the left, you can differentiate. So that's why the power is now 1 less. The same holds for moment, so you can imagine that if you also look into this problem here, for any point after A, your moment would be m0, and for any point before A, your moment would be 0. And this is your moment function. Now, again, similar to before, you can express that using the shear force, but then you need to use power minus 1 or distributed load using the power minus 2. So what I'm trying to say is that if you want to think about it, everything here is much easier to interpret. These are to keep the picture basically uniform and coherent. But in any case, now you learned how to handle the so-called discontinuity functions. What we want to do next is to solve exercise 3 using this approach. This approach that we do here is also sometimes referred to as double integration method. Exercise 4 of this lecture is similar again to problem 12.3 on page 586 of the book, except that now we want to solve this problem using the so-called discontinuity functions. The problem is exactly as we had before: determine the equation of the elastic curve for the beam shown in the figure and also the maximum deflection. EI is constant. Again, the difference only here is that we are assumed or we are enforced to use the discontinuity functions. So again, similar to before, we would calculate first the reactions at the supports. And using that, you would already know that if you wanted to calculate the shear force diagram or moment diagram, for any point between AB, the shear force would be 2, and for any point between B and C, the shear force would be -4. So based on this information, based on the shear force itself, all you have to do is to write the shear force function in terms of Macaulay brackets. So these Macaulay brackets that we have here basically tells you that if x is less than 2, you just get 0 from the second part. So if x is less than 2, V would be, or shear force would be simply 2, which is perfect. And if x is greater or equal to or larger than 2 here, then the expression here would be x minus 2 to the power 0, which gives you 1. So for any point larger than 2, then you get shear force of -4, which is exactly what we want. So this is possibly the most important and the most crucial part of the discontinuity functions and how you need to use them. If you write this one line correctly, the rest is fairly simple. So what you need to do next is to just integrate the shear force to get the moment itself. If you do that, now the integral of 2 is 2x. Integral of x minus 2 to power 0 is x minus 2 to power 1 times 6 plus a constant c1. The constant c1, you can assume it is 0 because at x equals 0, moment is 0. Because the support is just a pin and it does not apply a moment. So basically, if you insert just m equals 0 at x 0, you just see that c1 is 0 because you would get 0 from these two parts anyway. All right, so once you have now your moment function, which is exactly 2x minus Macauy brackets of x minus 2 times 6, all you have to do is to just proceed with our usual integrations. So this is your EI v double prime. And now you proceed with integration using the integration rules of Macaulay brackets for n power larger than 0, because here is 1. So if you integrate this thing once, instead of 2x, or the integral of 2x would be x squared, integral of x minus 2 to the power 1 would be x minus 2 power 2 divided by 2. So instead of 6, you would get 3 plus a coefficient c2. And then if you integrate again, you would have your function for deflection. All you have to do now is to insert your boundary conditions to compute the constants. And pay attention that you actually have two ends at which you know the deflection is 0. And you have exactly two unknowns. So what you want to do is to say deflection at 0 is 0, deflection at 3 is 0. You insert there, and you get C3 and C2. So once you have the constants, you can now write your deflection using the Macaulay bracket here. So basically, this tells you that if x is less than 2, this term will not contribute, and this would be your deflection function. And after x equals 2, or if x is greater equal to, then this would be your deflection function for the whole thing. So this is all you have to do. Again, once you have the deflection function, obviously you can calculate its derivative. You can set it to 0 to calculate the maximum deflection like we did. But the important thing here is that you can calculate the deflection function without splitting the coordinate like we did in the previous example. So previously, when we wanted to calculate this, we splitted the domain into x1 part and x2 part, but now you don't have to do that. You can actually write it in terms of just one coherent function in one line. All right, the next topic we want to talk about is the method of superposition. So the method of superposition is no different from what we have learned before. The idea here is that we are dealing with linear systems, and because of the keyword linear here, we are allowed to use the properties of linear functions. In other words, if you have a system like this, where you have a loading or a distributed loading W, and then you have a single force F, you are allowed to basically split this into two systems, system 1 and system 2, where in system 1, you only apply the distributed load, and in system 2, you only apply the single force. You can then calculate the deflection function for system 1, and you can calculate the deflection function for system 2, and your total deflection would be the sum of deflection from system 1 plus system 2. Now, obviously, if you can do it for the deflection, you can also do it for the derivative of the deflection, which is the angle. So this is the key idea of superposition. Basically, due to the linearity property, and if you remember, linearity here would mean that, for instance, f of x plus y is the same as f of x plus f of y, and then the other property would be f of a times x would be a times f of x. So if a function has these two properties, we would call that function linear, and these properties are valid for our analysis here in Mechanics and Materials 1, and that allows us to use the method of superposition, or that basically is equivalent to the method of superposition here. Now, you may ask yourself, okay, so what's the use of it? What's the advantage of splitting a system like this into two systems? So there are two advantages. The first advantage is that maybe you would be able to solve each system more efficiently if it is less complicated. But the second advantage is that usually there are handbooks, and in this case, the appendix C in your book, where you can find the solutions for simple problems or for simple configurations. So appendix C has two tables. In the first table, you find the solutions for simply supported beams. For instance, if you have a simply supported beam like this with the force exactly in the center, you can imagine that the maximum angle would be at the ends and the maximum deflection would be exactly in the center. So you can calculate those using our formula and integrating that twice and using the boundary conditions, obviously. But also in this table, you already have theta max here. You have maximum deflection. Not only you have those, you also have the elastic curve itself. But even if the force is not exactly in the center, again, you can find the solutions here. Also, if you have just a moment at the end, or if you have a distributed load, or a distributed load which starts from the beginning but comes only to the half, or a linearly increasing distributed load. So for these quite basically standard cases, simple cases, you already have the solutions in the table, and then if you can split a complex system into multiple simple systems, then you can maybe take advantage of this table. Also, I need to bring your attention that once you have, for instance, a uniform distributed load and a linearly increasing distributed load, you can imagine if you had a distributed load that was, for instance, linearly decreasing. This case does not exist in the table, but you can imagine you can basically construct this by assuming that you have a system with a uniform load and then subtract a linearly increasing load from that. So if you take this with a minus sign, this with a plus sign, and you add the response of those two together, you can basically take, or you can get into this case. Okay, so basically the idea is that you can use the method of superposition, obviously within the table itself, or combining different rows of the table. So in each row you see a different answer, and then in the next part of the appendix C, you see the distribution of, or basically the elastic curve or the deflection for cantilevered beams. Again, you have the standard cases where you have a cantilevered beam with just a single force at the end, or a single force exactly in the middle, distributed load, just one single moment, or a distributed load which comes to the half, or a linearly decreasing distributed load. And then again, as before, if, for instance, if you take these two cases together, you can, if you need, you can construct a case where you would have a linearly increasing load if you wanted to. All right, so this is basically why we learned about the method of superposition. And as I mentioned, if you use that method of superposition in conjunction with this appendix C, you can actually solve problems quite fast. And it's anyway a good alternative to what we have done before, but you should always think of it as an alternative. It's not necessarily something you have to use or using these tables. It's an alternative to help you. Before I jump to the next topic, I want to bring your attention to one of the equations here. So if you have a cantilevered beam and you apply a moment m, the angle that you have at the end, or the maximum angle, is ml divided by EI. Now this is interesting because if you remember, when we talked about axial loading, we had this formula delta equals PL over EA. When we talked about torsion, we had the angle of twist, phi equals TL divided by GJ. And now if you have a bending problem, you can actually see that theta, at least for this simple case, you can see clearly, it takes a form that is ML divided by EI. So you can appreciate the similarity of these formulations together. You get the length L here. The loading type, so if it's axial loading, it's a force P. If it's torsion, it's a torque T. If it's bending, is a moment M. The stiffness, basically, here would be elastic modulus E, shear modulus G, and then again in bending problem, because we deal with normal stresses, it's again elastic modulus E, and then in axial loading, area would come in the denominator. In torsion, remember, we had polar moment of inertia, and now we have the moment of inertia. All right, so it's good to just see all of these in kind of one picture to get the unified picture in mind. All right, so the next topic we want to talk about is statically indeterminate beams and shafts. Again, the term statically indeterminate in this type of problems, similar to the previous problems, exactly identifies that we have more unknowns than static equilibrium equations. So our static equilibrium equations, as always, are equilibrium of forces and moments. So in 3D, you have 6 equations. In 2D, you have 3 equations. But then that means if in a 2D problem you have more than 3 unknowns, that would be an statically indeterminate system. An example of that is, for instance, here. So the system on the left, it gives you 3 unknowns. But the system on the right, if you do not have a roller on the right, so you just replace that roller by a pin, by a joint, you get 4 unknowns. So a roller support has 1 unknown, but the hinge here, it has 2 unknowns, and that 1 extra unknown, it makes the right system statically indeterminate. If you think of a cantilevered beam, is a similar story. So the system on the left, it's statically determined because you have exactly 3 unknowns. On the right, you have those 3 unknowns plus 1 unknown due to the roller. So it's 4 unknowns statically indeterminate. But we talked already enough about statically indeterminate in the past. For instance, when we had an axial loading problem, we learned how to calculate the supports reactions for a axial loading problem which was statically indeterminate. Then we also talked about torsion problem that were statically indeterminate, but then again also then we talked about calculating the reactions at the support, and also we talked even about the bending problem itself, the problem that we talk about. So if you want to compute the reactions at the supports, this could be our new type of statically indeterminate problem. So this is what we want to do. How to calculate the reactions at the supports. In order to do that, we do exactly the same thing as we would do always. The first step is equilibrium, is basically drawing the free body diagram and write your equilibrium equations, or as many equations as you have, and it is valid. And then the missing equations, the part that we cannot basically solve using our statically equilibrium equations, will be solved using compatibility. So if you remember, for instance, when we had axial loading, the compatibility would be that if you think of a delta of the left part and delta of the right part, you can imagine they must be equal. So that would be your compatibility equation. For a torsion problem was the same. If you have an angle of twist here, you would know that the angle of twist would be the same. Now, for a bending problem, those compatibility equations, they can take different forms. But for instance, you can imagine that you can think of elastic curve, and then you know the elastic curve is a continuous curve. So at any point, you can imagine that the left and right deflections, for instance, would be equal, or their derivatives would be equal, because the tangents are also equal. On top of that, if you calculate the elastic curve, you can also impose the boundary conditions from the problem, so they give you also the additional conditions. And usually, this is how you would need to solve the problems. So you write your equilibrium equations, and then if they are not enough, you write your elastic curve, and then you use the compatibility of elastic curve to proceed. Now you use that compatibility maybe internally. So for instance, it could be right portion and left portion of the beam, or it could be just compatibility with the boundary conditions. We will learn that in a few examples together just now. Exercise 5 in this lecture is similar to problem 1217 on page 633 of the book. For the beam shown in the figure, determine the reactions at A and B. And then again, you can assume EA is constant. Now, if you look at the beam, you can clearly see that it's statically indeterminate because it is clamped on the right-hand side. So you would get 3 reactions already at B, but also you have 1 reaction at A. So we have a statically indeterminate system, and we need to calculate the reactions at the supports. In order to do that, we proceed exactly as we spoke about it. So we will write our equilibrium equations, obviously, but we can also use, not that we can, we should also use our elastic curve as the additional equation helping us to solve for the problem. So if you start from the left-hand side, here you have AY, which obviously we don't know what it is. But if you cut the beam at a distance x, you can calculate the shear force and moment based on that. And then again, in this particular example right now, we are not interested in the shear force itself. We are interested in the moment as a function of x, because later we know that EIV double prime would be m, and if you integrate that twice, you get your deflection. That's what we want. Now, if you look at this triangle, so basically it's, if you cut it somewhere here, this would be a triangle that we have there. The height of that triangle would be W0 divided by L times x. So again, W0 divided by L is clearly the slope of the line times x, that gives you the height. Here the width or the base is x. And basically the area of the triangle would be 1/2 of W0 x squared divided by L at the distance x over 3 from the right hand side. And then the force AY is upwards, or we assume it's upwards. If you multiply it by x, it also causes a moment. So if you write the equilibrium of moments basically to be 0 at this point, or with respect to the point here, you would have m plus 1/3 x times 1/2 of W0 x squared divided by L minus x times AY equals 0. And from that, you can get your moment equation. So if you have now moment as a function of x, all you need to do is to set moment equals EIV double prime. Then you integrate that once to get v prime, and you integrate twice to get your deflection function v. Now you can see that you have 2 unknowns here that are the constants, but also you have AY itself as unknown of the problem. So we don't know what AY is either. But it's not a big problem, because if we have 3 boundary conditions, or if we use 3 boundary conditions, we can solve for these three unknowns. And that's what we want to do. So for the problem that we have here, we know deflection at A is 0. So at the right A, the deflection is 0 because you have that roller support. And on the right-hand side, the deflection and the derivative of deflection, they both are 0. So this was the problem. So basically, you know here on the right-hand side, V is 0, V prime is 0, and on the left-hand side, the deflection itself is 0. So you have these three boundary conditions, you have three unknowns, and from that, you can calculate those three unknowns. Now, once you have these, and in particular this, then you have your two equilibrium equations, which you have not used yet, for the entire system. So if we draw the free body diagram for the entire system, and those two equilibrium equations, then they give you By, and they give you the moment at B. So if you use them, then the force By would be, or the support reaction at B would be also calculated. There is a force and there is a moment from the support. Okay, so that is basically how you would solve a statically indeterminate problem. And you can see that in this slide, you can see everything that we did. So you calculate M based on Ay, which is unknown, but then from that, you calculate the deflection. In the deflection function, you would have that unknown, but then using boundary conditions, you can eventually calculate that unknown, and then using your additional equilibriums, you calculate the reactions at the other support. What we want to do next is to solve this exact problem using the principle of superposition. So alternatively, we want to do that if we use the principle of superposition and the tables that we had in Appendix C, how we can approach this problem. So we want to look at the same problem again using the principle of superposition now. So in order to do that, you can imagine that basically we would say the system that you have here, it can be decomposed into system 1 and system 2. In the system 1, in the first system, you just have the distributed load, but you omit the support reaction for system 1. For system 2, you just include the support reaction. So now you can imagine for the first system, you would get a deflection at point A. And for the second system, you also get a deflection at point A. But then you know that the total deflection at point A is 0. And that would be your compatibility equation. So you can write the total deflection at A is 0, but then total deflection is the deflection due to the system 1 and due to system 2. And now from the table, because these two systems are now simple and standard, from the table or from Appendix C, you can calculate the deflections for each of the systems. And all you have to do is to then insert these into the equation here, and from that compatibility, you can calculate Ay, which is exactly what we calculated previously using our classical approach. So as you can see, if you can use the method of superposition carefully, the solution procedure is sort of more compact, especially if you use it in conjunction with the tables in Appendix C of the book. Exercise 6 and the last exercise of today's lecture is similar to problem 1222 on page 648. For the beam and rod system shown in the figure, determine the force in the rod due to the loading. For both members, elastic modulus is given as 210 gigapascal, and for the beam, the moment of inertia I is 186 times 10 to the power 6 millimeter to the power 4. So the system is composed of a cantilevered beam. It's a 4-meter beam with a force of 40 kilonewton downwards at the center. It is connected to a rod at the end, to the rod BC, with the height 3 meters and the diameter 12 millimeters. What you are asked to do is to calculate the force in the rod. So if you look at the beam alone, you can see it's a cantilevered beam. So you have 3 unknowns on the support A, but then you also have your force at B or By or Fb, and basically you have 4 unknowns. So the beam alone is a statically indeterminate system. What you need to do is to assume or to impose the constraint that it is connected to a rod as the additional compatibility equation that otherwise you are missing. So you have 4 unknowns, but you have your usual equations, the 3 equations of equilibrium, equilibrium in the x direction, in the y direction, and equilibrium of moments. Now, equilibrium of forces in the x direction, it gives you Ax equals 0. Equilibrium of the forces in the y direction, it gives you Fa plus Fb equals 40 kilonewton. And the equilibrium of moments reads Ma equals 4Fb minus 80. So 80 is again 2 times 40, and 4Fb would be the moment due to the force Fb at the other end. All right, so basically if you look at the beam alone now, I already omitted the axial force Ax. You have a beam with 3 unknowns and 2 equations. So we cannot solve this. What we need to do on the other hand is to calculate the deflection. And if you calculate the deflection using the constraint that it is connected to a rod, then maybe you would be able to solve the problem. So in order to solve for the deflection, we start with the shear force. Here you have Fa upwards. So you can imagine that if you cut the beam at any section before the point in the center, the shear force would be Fa. So if x is less than 2, the shear force would be just Fa. And if x is larger than 2, the shear force would be Fa. So the shear force would be Fa minus 40. Okay, so the shear force is Fa minus 40 anywhere here, and is simply Fa here. So in order to write that as one function, we can use the Maculi brackets, and that's how it is written. So that's your shear force distribution. And now if you integrate your shear force, you get the moment. And in your moment equation, you would basically get the integral plus a constant. Now you know that constant, let's call it C star, that constant C star would be basically the same as the moment at 0, because you can see that if you use the coordinate 0 here, you get 0 for both arguments. So basically the constant at the end is nothing but your moment at 0, which is exactly Ma. So that's why you have Ma here as the usual constant C. Okay, so once you have that, all you need to do is to insert your moment equation into our typical deflection equation. So Ei v double prime equals m, and then m is just what we had here. Now you need to integrate that once to get v prime, and integrate twice to get the deflection function v itself. Now you can see that you have two unknowns, C1, C2, but also you have MA, which is an unknown. So there are three unknowns. They are not actually two unknowns. So the first thing we do is to impose the boundary conditions. So we have two boundary conditions here. We know V is 0 at A and V prime is 0. So if you impose those, you can actually see that if V prime is 0, everything would be 0. So C1 would be actually 0. And then again, because at 0, V is also 0, then C2 is also 0. Okay, so C1 and C2 are 0, but still we have MA as one extra unknown. In order to calculate that, we need to look at the boundary condition at B. But the boundary condition at B is slightly non-standard because it's connected to a beam. So basically what you have there is only this. You can only say the deflection at B, so V at x equals 4, is minus FBL divided by EA. So pay attention that the minus comes because of the difference in the signs. So if you imagine the deformation, the elongation of a beam under a force P downwards, it would be PL over EA. But then that elongation basically requires a downward force. So basically what happens here is that the delta at B that you calculate for the rod, it has a different sign from the deflection at B. In other words, if you assume, I think this is the easier way to explain it. If you assume this is what is happening, the rod is under elongation, so the delta for the rod would be positive, but then this means that the deflection itself is negative because it's downwards. It's different from our convention. So for that matter, basically, you need to just be careful and use a sign difference here, a minus sign, because we assume here that FB is upwards, and then the upward deflection would mean a compression in the rod. Okay, so this is your fourth constraint basically. Now from the first two constraints, as I mentioned, C1 and C2 would be 0. And what we want to do next is to use this constraint. So in order to do that, all you have to do is to take your deflection equation and insert x equals 4 in your deflection equation, which you get this. And then equate that to your rod deformation. So basically what you have now is this. This is your third equation. You had two equations here, and you have exactly 3 unknowns. So you would be able to solve this. So all you have to do then is to insert the equations or the red equations into the orange equation, or at least we can start with the balance of forces. So you can see from that equation that FA is 40 minus FB, and from the other equation you can see that MA is 4FB minus 80. So if you insert those values, you would have one equation in terms of FB, and then again this part is basically your contribution, or the part that is related to the beam, to the rod, and A would be the diameter, A would be the area of the rod, which is pi r squared, and r would be half the diameter. Diameter is 12 millimeters. So basically, if you do that, you get your force FB, which is 10.15 kilonewton. Okay, so this is how you need to solve this basically. Again, if I just go 2 slides or 3 slides back, this is really the crucial step here. All you want to do is to calculate V from this equation. Well, pay attention that you need to divide it by EI. You calculate V from that equation, and then you insert that, and then again, this is EIV, that's why we have an I here. So this is your deflection, and this is basically the corresponding values from this. So this is EIV, and this is essentially your EI times minus FB L divided by EA. You equate them, and then the rest is to just solve the equations. Okay, this would be your FB. This is what the problem wanted us to solve. But before we finalize this, we want to alternatively solve this using the method of superposition. And you will see how simpler it gets with the method of superposition. So if you want to look at this problem using the principle of superposition, you can split the system into 2 systems. So the first system, the green system, would be basically a beam under a force of 40 kilonewton at the center. And for that system, you can calculate your delta, deflection. The second system would be a beam under a force of FB at the end. And for that system, you can also calculate the deflection at point B, which is this. Now, the deflection of the point B itself, though, it's minus FBL divided by EA. And then again, minus comes just from the fact that we know that if delta is larger than 0, so if delta is elongation, your deflection of the beam would be negative. So basically, all you need to do now is to say delta at point B, which is the change of the length of the rod, is the deflection of B from system 1 plus deflection of B from system 2. So if you do that, basically in one step, you can calculate your FB to be 10.15 kilonewton. Obviously, I'm not showing you the calculations, but it's very simple. All you have to do is to insert just these values into this equation. All right, now you can see that for this particular problem, at least using the method of, or the principle of superposition is significantly helpful to analyze a statically indeterminate system. All right, this was our lecture on the topic deflection of beams and shafts. We covered the whole chapter 12, and that's why it got a bit longer than our usual lectures. In particular, we covered sections 12.1 to 12.3, 12.5 to 12.7, and 12.9. What we want to do in the next lecture is to kind of go back. We go to chapter 7, and we will talk about transverse shear. I'll catch you in the next one.